Recording. All right, so welcome back, everyone. All right, so here's where we are right now. Okay, so today is Monday, October 12th. All right, we're going to continue with continuous distributions, lesson 21, and starting lesson 22. And we'll continue with that next time. All right, lesson 22 is on the central limit theorem. That's going to take some time. As it suggests, the name central limit theorem is pretty important. I'm going to break that up in two. Okay, now remember that all of this third homework assignment from lessons 19 through 23, that's going to be due Thursday of next week, which is Thursday, October 22nd. Okay. Also, next week, Friday, is the withdrawal deadline, Friday, October 23rd. So obviously, I'm going to make a push to at least get homework 1 graded by then. Even to be honest, even the first week of October was pretty heinous, but I'm finally on track and I'm starting to grade this stuff. So I'll have at least the first homework assignment graded by the withdrawal deadline, obviously. So anyway, that's the third homework assignment due Thursday, October 22nd. Withdrawal deadline is the next day. All right, and we'll do the homework session for 3. Well, basically next week we're going to devote to covering the homework. All right. So question session next Monday and the answer session next or Wednesday of next week. Okay. But this week it's pretty dense. I mean, it's pretty intense, deep video. So I hope you had your coffee or tea. All right. I know I have. And we're going to go through a lot of this dense material this week, and we'll talk about it next week. All right. So any questions before we proceed? We have much to do. We have much to do. All right. So let's start. And feel free to ask questions in chat. Let's start. We are recording. All right. Feel free to chat. Here we go.
Hi, everyone. Last time we talked about the standard normal distribution, which is indicated by this bell-shaped probability density curve. The standard normal distribution is a special kind of normal distribution with mean 0 and standard deviation 1. But what about normal distributions in general, with a general mean mu, which could be 0 or something else, and standard deviation sigma, which could be 1 or something else, positive? We're now going to talk about normal distributions in general. What if a normal isn't, for example, the standard normal distribution? All right, well, here's the key thing. We're going to be doing conversions where we're basically changing from this picture, from the general normal, over to this picture with the standard normal. So we're going to get things down to z-scores. We've done this before. Part A, standardizing normal scores. That means finding z-scores to find probabilities. Assume that X has a normal distribution with mean mu and standard deviation sigma. Here's the shorthand. X has as its distribution a normal distribution with mean mu and standard dev sigma. Now, in general, mu and sigma, the mean and the standard dev, could have any units: points, inches, feet, pounds, light years, and so on. But do make sure that mu and sigma are written using the same units. So, for example, mu should not be in feet while sigma is in light years. That should not happen. On the homework, I will not trick you like that. Now, we're assuming that X has a general normal distribution. When I write down Z, I'm going to assume that Z has a standard normal distribution, meaning that Z has, as its distribution, a normal distribution with mean 0 and standard dev 1, the standard normal. Z-scores have no units, so these are not going to be in feet or light years or whatever. They have no units. So again, the idea is that we're going to be changing from the normal distribution in general to the standard normal distribution. We're going to engage in a standardizing conversion process. To find probabilities for values of X, which have the general normal distribution, we need to transform or convert from X scores to Z scores. We're going from a general normal distribution to a standard normal distribution. and we're going to use our usual formula for z-scores. Remember how we calculate z-scores. You take the original x score, subtract off the mean, and then divide by the standard deviation. If we have population data, we have this format, x minus mu all over sigma. And we usually round off. Again, in this process, when we subtract off the mean from all the data points, then we end up with a new data set with a mean of 0. When we divide by the standard deviation, we end up with a new data set with a standard deviation of 1. That's what we did early on in the semester. We're now going from data sets to distributions in general. In this case, we're talking about normal distributions. And we're standardizing from a general normal distribution, where these guys come from, to a standard normal distribution, where these z guys come from. So again, we're going to use that formula to convert from these various normal distributions, which could have various means and standard deviations, to the standard normal distribution, the standard normal distribution. There's only one of these guys. The normal distribution with mean 0 and standard deviation 1. Z-scores higher than 0 indicate that you're above the mean, which was the case beforehand. A z-score below 0 means that you have a score that's below the mean, which was the case beforehand with the general normal. We're going to talk about specific examples next time.
All right, any questions before we go on? Any questions before we go on? We dealt with the standard normal distribution before. We're generalizing it now to more general normal distributions. Mean, whatever, standard dev, whatever. All right, any questions? All right.
Hi, everyone. Let's continue with lesson 21 on general normal distribution.
By the way, notice it's a long video, 21 minutes, so feel free to chat if you have questions.
Let's do some examples. All right. Let's say that x is the height of a random American woman. Then x has, as its distribution, a normal distribution with mean mu being 65 inches and standard deviation sigma being 3.5 inches. Notice these are in the same unit. And there's a source for this. Now, as two key hints for you, these are two key hints regarding the z distribution. This basically says that the probability that z is less than negative 1.43 is this, 0.06764. And the probability that z is less than 2 is this, 0.9772. Two key hints. And by the way, we can verify this with tutorhomework.com. Okay, so what's the left tail probability for negative 1.43? Left tail, negative 1.43, go to probability, and we see 0.0764, which is verified here. For z equals 2, we get 0.9772. So that verifies this value over here. Two key hints. So as you do your work for this example, make sure that you do connect up with these hints. Otherwise, you've made a mistake. Part A, find the probability that x, which is the height of a random American woman. So let's say that we take a random American woman, find the probability that her height is less than 60 inches, or 5 feet. First, we're going to write the corresponding probability expression for z. I want you to standardize. So notice that on the tutor homework site, it is expecting you to standardize because it's working with z-scores, not x-scores. All right, and we're going to show work by using the formula for z-scores. We take our boundary value here, 60 inches. Sometimes we have two boundary values. In this case, in part A, we only have one, 60 inches. And we need to use this information for this normal distribution to standardize this x-score and turn it into a z-score for a standard normal distribution. All right, so to do that, solution. To find the probability that x, this random woman's height, is less than 60 inches, take the boundary score, x-score, 60 inches, and transform it into a z-score by using the formula for z-scores. So we go from here to z equals negative 1.43, and that's where the hint comes in. How do we get negative 1.43? Well, here's our formula for z-scores. You take the original x-score, subtract off the mean, divide that difference by sigma, the standard dev. Our original x-score was 60. The mean is 65. The standard dev is 3.5. And all of these are in inches. So these are all compatible units. They're all in inches. And in the end, we're basically dividing inches by inches, and the z-score has no unit. So when you,
By the way, you must show this work on the homework. You must show like 60 minus 65 all over 3.5. You must show that work. Okay, because come on, that's in the hint, right? The number's in the hint.
to work out this fraction, make sure to process the numerator first. It's negative 5. You end up with about negative 1.43 to two decimal places. That's our z-score, about negative 1.43. And as we dictate in the problem, you need to write the corresponding probability expression for z, the standard normal random variable. So from here, the probability that x is less than 60 inches, that's going to be about the probability that z, the standard normal z, is less than negative 1.43, which is the z-score for 60 inches. I say about because remember, this was an approximation, negative 1.43. We're rounding off. Although I won't mark off if you put equals. So we want the left tail probability, and from either tutorhomework.com, we can see it's 0.0764. That's the approximate probability to 4 decimal places. Or remember, I gave the hint. That left tail probability, the cumulative probability to the left of negative 1.43, this area is 0.0764 for the shaded region. So that is our answer, 0.0764. So there's about a 7.64% chance that this random adult American woman is shorter than 60 inches or 5 feet. Okay, the next question, the next part, find the probability that this random adult American woman is taller than 60 inches or 5 feet. And we're going to write the corresponding probability expression for z, the standard normal. To work out that part, to find the probability that this random adult woman is taller than 60 inches. Well, wait a minute. In part A, we're asking the question, what's the probability that this woman was shorter than 60 inches? We found that was 0.0764. So if we're asking for the probability that the random woman is taller than 60 inches, we want the complement. Remember, it doesn't matter if there's a bar there or not. Well, how do we find the complement? Consider the overall density curve. Okay, the overall density curve has underneath it an area or total probability of 1. We found out in the last example, or in our hint, that the left tail probability was 0.0764. That's the area of this white region over here. But the shaded region is the area that I want. This area is going to be 1 minus the 0.0764. So the probability that x is greater than 60 inches, that's about the probability that z is greater than negative 1.43. That's the probability expression in terms of z. We want the complement. We want 1 minus the probability that z is less than negative 1.43. You don't have to write this part down if you write this. If you go ahead and plug in that the left tail probability is 0.0764. 1 minus 0.0764, that's this probability over here. I'll mark it. 1 minus this is going to be this, which is our answer.
So yes, I got a question, a common question. If I ask for a picture, then I do want something like this, and you should shade, right? So even an arrow may not be quite enough. I often do want the actual shading of the actual area or probability that we want. So please keep that in mind. Read the question carefully.
About 0.9236. On tutorhomework.com, that'll be the right tail probability, 0.9236. So the probability that a random American adult woman is taller than 60 inches or 5 feet is about 92.36%. Okay. Next up, part C. Find the probability that this random adult American woman is between 60 inches and 72 inches. So between 5 feet and 6 feet. The probability that this random adult American woman is between 5 feet tall and 6 feet tall. Again, we're going to write the corresponding probability expression for Z and use the formula for Z-scores when showing work. Well, our first step is to find the Z-scores for both of these two boundary values, this lower value and this upper value. So we take the boundary X scores, 60 inches and 72 inches, and transform them into Z-scores. So first off, for 60 inches, we use this formula for Z-score, X minus mu all over sigma, okay? We take the 60 inches for X, subtract off the mean, 65 inches, divide the difference by the standard dev sigma, which was 3.5 inches. The result is negative 1.43. This was the same calculation we did in part A. Now for 72 inches, that's the new piece of information we have to find. For 72 inches, let's find the Z-score for that. It's the same Z-score formula. This time we plug in 72 inches for the upper left. But since we know these are all in inches, we don't even have to bother with units here. We subtract off 65. That's the mean for the distribution. Divide the difference by the standard dev, 3.5. The result is about 2.00 to 2 decimal places. So the corresponding probability expression for Z looks like this. The probability that X is between 60 inches and 72 inches, between 5 feet and 6 feet, the corresponding probability expression for Z is this. The probability that Z is between negative 1.43, which corresponded to this, and 2.00, which corresponded to that. Remember, for an in-between probability, we subtract probabilities. And again, we got the hints from before. So remember the hints. We have the two hints here. The probability to the left of 2.00 was 0.9772. The probability, the smaller probability, to the left of negative 1.43 was 0.0764. And we have to subtract these two probabilities to get the middle in-between probability, or area. So again, we take the 0.9772, take the 0.0764, subtract these two probabilities in order, the greater minus the smaller, and we get our final answer, which is 0.9008, or about 90.08%. So there's about a 90.08% chance that this random adult American woman is between 5 feet and 6 feet tall, or between 60 inches and 72 inches tall. Okay, now before I forget, I'm going to go ahead and show you how to do a calculation using Excel. So let's say we go back to Excel and consider this probability. The probability that X is less than 60 inches, assuming that X has this distribution up here. Mean 65 inches, standard D 3.5 inches, normal. All right, let's go to Excel. So again, we want to find the probability that X is less than 60 inches if X is distributed as a normal with mean 65 inches and standard dev 3.5 inches. Now we could convert to Z-scores, and then this will confirm what we got from the website, norm.dist. The Z-score of negative 1.43, if we look to the left, that probability is about 0.0764, okay, which is confirmed by the picture over here. Now, the tutorhomework.com website assumes that you know how to standardize and find Z-scores. Excel is more liberal. Excel allows you to work directly with the original X distribution. Still, it's good to know how to convert though, folks. It's good to know how to convert. But Excel is more liberal. What is the left tail probability for x equals 60 inches if the mean of the distribution was 65 inches and the standard dev was 3.5 inches? Again, since we have consistent units, we don't have to put units in Excel. We want the cumulative probability. Well, it's the same as what we got from before, about 0.076. I'm a little bit off. Oh, yes, I'm a little bit off because of rounding error. Yeah, because the z-score was about negative 1.43. But if you were a bit more precise, if you used a more precise z-score, then you'd get about 0.0766. We can chalk that up to rounding error when we rounded off the z-score to 2 decimal places. Okay. Now, let's deal with the inverse problem. Given a probability, how do we find the corresponding x-score? Once again, we go through z. All right. So here's the formula that takes us from mu to x.
From z to x.
All right. And we get that by taking our formula from x to z. So here's the deal. Back when we were converting from x to z, we use this formula over here, our classic formula for finding z-scores. What I'm doing here is I'm going to derive a formula to take you from z back to x. All right. And we're going to prove this formula over here. So if you remember your algebra, we take this formula here. We're solving for x. What do? We multiply by sigma on both sides. So we get z times sigma equals x minus mu. That bottom now disappears. We're still solving for x. To solve for x, we add mu, the mean, to both sides. I'll put on the left here. Mu plus z sigma equals x. Turn it around. X equals mu plus z sigma. Which does make intuitive sense because here's the idea. You're starting at the mean. What happens if you walk mean? Make the tail a little bit bigger. Okay. What happens if you walk z standard deviations away from the mean? So let's say z is positive. If you walk, say, 1 standard deviation away from the mean, then maybe you're here. If you walk 2 standard deviations away, maybe you're here, and so forth. So this formula should make sense. You start at the mean mu, and you walk z standard deviations away. If z is 0, you stay at the mean. If z is negative, you're walking to the left. So here's the formula that takes us from z to x. But now we're going to add on the wrinkle of probability. So before, we went from x to z, and then we went to probabilities. But now we're going to start with probabilities, describing a percentile. We're going to go to z-scores and then get the actual x score, which is really the percentile of the x distribution. So from the probability, we get a percentile for the z distribution, the corresponding percentile for the z distribution, and then the corresponding percentile for the x distribution. Let's do an example. Same distribution as before. We're going to consider, in example 2, x, which is the height of a random American woman. X has as its distribution a normal distribution with mean 65 inches and standard dev 3.5 inches, same as before. Now let's say that to join a particular basketball team, a woman has to be at least at the 85th percentile of heights of American adult women. So let's find the 85th percentile of this distribution of heights of American women, and we're going to round it off to the nearest 1/10 of an inch. That's 1 decimal place. And we're going to write the corresponding probability statement for x and interpret it. Okay. We're going to use a hint that we used in an earlier lesson, lesson 20, the fact that the 85th percentile for the z distribution was 1.04. If you go to the tutorhomework.com website, I'll clear these out. We want a left tail probability of 0.85. What's the corresponding z-score from right to left? About 1.04 to 2 decimal places. Back here in Excel, norm.inv, we're doing the inverse problem, going from probabilities to z-scores, about 1.04.
By the way, I'm going to give you the web link. Let me try to get the web link here. Yeah, here we go. I emailed this to you.
Okay, so we're going to use this hint. Okay. We first have to transform this x-score into we have to transform this z-score now into an x-score. Before, we were transforming x-scores to z-scores. Now we're transforming z-scores to x-scores. And we use that formula I just showed you. You take the mean and you walk z standard deviations away. The mean and the standard dev are in the same unit. Z-scores have no unit. We're basically doing inches plus inches. That'll give us inches. All right, although you should write the unit in the final answer. So the mean was 65. The z-score we're looking at is 1.04. That's the 85th percentile for the z distribution. That's from the hint over here. The standard deviation is 3.5. So using a scientific calculator, say, which does the multiplication first before the addition, order of operations, we get 68.6 inches. Don't forget your unit, inches. Remember, z-scores have no units, but x-scores usually do. In this case, it's inches. You could even convert to feet. This would be 5 feet and 8.6 inches. Fairly tall. Remember, we're hiring for a basketball team. Although there is Mr. Bogues, he's fairly short, so you can also be short and be a good basketball player. So here's the picture for the x distribution. What is the x-score, the actual height, that gives us 85% or 0.85 area or probability to the left, the cumulative probability, about 68.6 inches. So an American woman who is 68.6 inches tall, about 5 feet, 8.6 inches tall, that woman will be taller than about 85% of all American adult women. Again, we can phrase it as a probability problem or a proportions problem. The probability that a random American woman is shorter than 68.6 inches is about 0.85 or 85%. Framing it as a proportion problem, the proportion of American women who are shorter than 68.6 inches tall is about 0.85. So you can phrase this as either a probability statement or a proportion statement. Okay, so here's the probability statement in terms of x. It's more accessible to stat students. The probability that x, the height of a random adult woman, is less than or shorter than 68.6 inches is about 0.85 or 85%. In plain English, for the layperson who hasn't taken stats yet, about 85% of American women are shorter than 68.6 inches. Or as a probability statement, the probability that a random American woman is shorter than 68.6 inches is about 85% or 0.85. But then you're sneaking in that word, probability. Okay, that's lesson 21. Next time, we're going to see another key application of normal distributions, aside from the fact that we see them a lot in practice, the central limit theorem. And it is as important as it sounds. We're going to use this to analyze means or averages. It's a big theorem. It's central. That's next time.
Okay, so before that key CLT, I'll go back to the statement there. Any questions before we go on? Okay, that concludes lesson 21 on general normal distributions. Any questions before we go on? All right, let's proceed.
Here's the probability statement in terms of x. It's as it sounds. We're going to use this to analyze means or averages. It's a big theorem. It's central. That's next time. Hi, everyone. Just a quick note on how to calculate percentiles on Excel. Back to example 2, where x is the height of a random American woman. X is normally distributed with mean 65 inches and standard dev 3.5 inches. We wanted to find the 85th percentile. So we discovered that, or we hinted that 1.04 was the 85th percentile of the z distribution. And we can find that out on tutorhomework.com. The 85th percentile, the z-score is 1.04. Or on Excel, this command, norm.inv 0.85 for the standard normal, mean 0, standard dev 1, it's about 1.04. But what about the x distribution? We discovered that it was about 68.6 inches by using this formula over here. Well, Excel does it pretty quickly. You don't have to go to z-scores on Excel. Here's the command, norm.inv. We're asking the inverse problem. We're going back from probabilities to x-scores this time. We want the 85th percentile, and we're looking at a general normal distribution with mean 65 inches and standard dev 3.5 inches. So we want the 85th percentile of this x distribution. The score x star such that the probability that this random x is less than x star is about 0.85 or 85%. So we put that in, equals norm.inv. We want the 85th percentile. The mean was 65, standard dev was 3.5, and we get about 68.6, and that's in inches. Again, the x-score should be in inches. So that's our Excel tip.
Okay. Although, folks, please do the formulas, okay? Please do the formula. I mean, if you can work Excel, that's great, but that's a side tip, okay? On your homework, don't tell me that Excel did this or that for you. Please show me the work. Show me using the formula, please. Any questions? Any questions?
Hi, everyone. We're going to start lesson 22 on the central limit theorem. And this theorem is really critical to analyzing averages or means. So later on, when we do hypothesis tests, for example, or confidence intervals to analyze means, we're going to appeal to the central limit theorem. All right. Now, in the beginning, let's start with our old experiment. Roll one die, this old classic experiment. We roll one standard six-sided die, and we're going to let x, this random variable, be the result of the die. We know that x has this probability distribution. It's a discrete uniform distribution. The probability of getting a 1 on the die is 1/6. The probability of getting a 2 on the die is 1/6, and so forth. The probability of getting a 3, a 4, a 5, a 6, each 1/6. This is a discrete uniform distribution, and for right now, let's call this distribution D. So X has as its distribution this discrete uniform distribution D. Later on, we're going to let D represent a more generic distribution. But for right now, let's say that D is this specific discrete uniform distribution, the result on one die. We saw this in a previous lesson. Okay, now here is a probability histogram. It's a flat top, discrete uniform, flat top. And again, we can relate probabilities with areas, right? So probability 1/6 here, 1/6 here, and so on. Total probability is 1. Now again, this is a discrete uniform distribution, but the ideas of this lesson will apply to all discrete and continuous distributions with a finite standard deviation, which we're going to assume. So don't worry, we're not going to have any examples in class with an infinite standard deviation. Basically, the ideas will apply to all distributions that we're going to deal with in this class. Okay, now using the formulas from lesson 16, that was back when we were dealing with expected value or the mean of a probability distribution. We can find that D has the following mean. Mu, the mean of this probability distribution, is 3.5. That comes from the zigzag. This times this, plus 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 this times this. It's the zigzag. But because we have a discrete uniform distribution, we could just as well add up these values and divide by 6. The old school way of finding a mean or average works here because we have a discrete uniform distribution. If this were not a uniform distribution, then we'd be forced to use the zigzag. Okay, but either way, from the zigzag or just adding these up and dividing by 6, we find that the mean is 3.5. Mu is 3.5. The standard deviation of this distribution, sigma, is about 1.7. Now, we did not discuss the calculation of these kinds of standard deviations in this class. This was part of the optional handwritten notes in lesson 16, back in the probability unit for the class. So we did not discuss how to compute this. But if you're curious about how to get the 1.7, then you can look back at the previous optional handwritten notes. You don't have to do that. You can take this on faith, that the standard deviation of this distribution is about 1.7. It's about this. All right, I have a comment here. When in doubt, round off to at least 5 significant figures. That's to just play it safe. Okay. Now, instead of a histogram, it turns out to be more convenient in this lesson to use a spike plot because, as it turns out, we're going to have many possibilities in these various examples. So here, remember that there are 6 possible values for x, the value of the die, and we have a probability mass of 1/6, or about 167 at each of these die faces. So about 0.167 or 1/6 probability mass at a die face of 1, the same for a die face of 2, and for 3, and for 4, and for 5, and for 6. Now, you might be wondering what this blue line is for down here, this blue line, labeled X bar. You might remember that X bar represented sample mean, basically an average. But in this case here, if you're rolling one die, then it's very easy. If you roll one die, then the average you get is just the result on that die. If you roll a 3, for example, right, and I ask you, what's the average so far on this die that you've rolled? You've just rolled it once. If it came up a 3, then your average so far is a 3. So really it's the same scale here, right? From 1 to 6, same values. Now later on, when we're rolling 2 dice, or 4 dice, or 8 dice, or so on, then you're going to see differences between the sum of the values of the dice and the average, or sample mean we get on the dice. But if you're just rolling one die, then the result on the one die, the sum, the average, the result, they're all the same, right? It could be some number, some integer from 1 to 6. Okay, so again, for one die, it is convenient that the die result, the sum, and the mean are all the same. If you roll a 3, that's the result, that's the sum, that's the sample mean. Later on, there will be distinctions. Okay, so now let's roll 2 dice. And that does make things a fair bit more complicated. It makes things 2-dimensional. Now, actually, we did do this experimentally in this class. So you may remember, I had people roll dice. Perhaps that was unhygienic. I apologize. But I had
this was a previous term before the virus.
people roll a red die and a green die. So for example, the first person rolled a 1 on the red die, a 4 on the green die. The total or sum was a 5. We're focusing on the sums in the end. The second person rolled a 4 on the red die, a 2 on the green die. The sum was a 6. So we got these various sums in black ink over here, black marker, and take a look at the results in black marker. Okay, so this was the sample sum as each student rolled a pair of dice. Take a look at these sums in black marker. Take a look at these sums. What do you notice about them? Now remember that sums can be between 2 and 12, right? Those are the possible sums for 2 dice. If you get snake eyes, 1 and 1, that's a sum of 2. I guess no one got a total of 2 here. If you get boxcars, 6 and 6, that's a sum of 12. Actually, the third person did get boxcars. 6 and 6 is 12. But if you look here, does it look like the distribution of sums is uniform? Does it look like the lower sums, the middle sums, and the higher sums are equally likely? And the answer seems to be no, because we only have a few 3s, 4s, and 5s, it seems, and we only have a few 10s, 11s, and 12s, it seems, but we get a whole bunch of 6s and 7s, and we have an 8 here. And in fact, when we did a frequency histogram, okay, well first I did a straight up count by tallies. This is a frequency table with tallies, okay? And here's a frequency histogram, the sums from 2 to 12. And when we did a frequency histogram, notice it was roughly triangular. It wasn't perfectly triangular. There was some sampling error, but notice that we tended to have like a peak in the middle and it sort of tailed off at the ends. Okay, so rolling 2 dice. We roll 2 standard 6-sided dice, 1 red and 1 green. Remember that made probabilities easier to calculate. We consider this to be a sample of size n equals 2 from the original distribution D for 1 die. So remember, the original distribution D looks like this, basically a flat top, right? Okay, this is the original discrete uniform distribution for rolling 1 die. Now, take the first student, say. The first student rolled 2 dice. So basically, the student was taking a sample of size 2 from this same distribution, this same flat top distribution, a sample of size 2. And in fact, each student was taking a sample of size 2 from this distribution. Each student rolled 2 dice. Let x sub 1 be the result of the red die. Let x sub 2 be the result of the green die. So both x sub 1 and x sub 2, the result of each die, has this original Big Daddy D distribution, this flat top, uniform. All right. But now we're going to consider the distribution for the sum of the 2 dice. Summation x, x sub 1 plus x sub 2, the sample sum or total of the dice. If you're in Vegas and you're rolling a pair of dice, you usually care not so much about the red die versus the green die, but what was the sum of the 2 dice. So for example, if you roll a 3 and a 4, then the sum is 7. Who knows, maybe that's craps. Okay. Likewise, in addition to a sample sum, we can also talk about a sample mean or average. It's a capital X bar here because it's a random variable. It'll vary depending on what the student gets, right? Okay, so the sample mean here is a random variable. Let's say I go to the first student. I don't know yet what the first student is going to roll. So X bar, the sample mean or average for the 2 dice that the student will roll, I don't know the value of this yet because I don't know the value of X1 and X2 just yet. But I do know that eventually when the student rolls the red die and the green die, and when we get results for X sub 1 and X sub 2, I think the first student got a 4 for X sub 1 and a 1 for X sub 2, then we could compute the sample mean or average. If the student rolled a 4 and a 1, then the average is 5/2 or 2.5. The average of 4 and 1 is 2.5, and that would be the value of X bar for the first student. Each student rolls a pair of dice. Each student gets a sample sum, and each student gets a sample mean. And of course, we expect them to have some differences. Some students rolled smaller sums, some rolled medium sums, some rolled larger sums. And therefore, some students got lower means, some got middle means, some got higher means. Notice I said middle means. Yes, there is the idea of a mean of means. We're going to talk about that. Okay, so for each student, we have this random variable. Well, summation x, that's a random variable, and also x bar, that's another random variable. All right. Now let's consider the distribution of the sums and the sample means, the sample sums and the sample means. Okay, Well, let's look at the various possibilities. We've looked at these tables before. Let's look at the possible sums that we can get on a pair of dice. The red die can come up any integer from 1 through 6. The green die can come up any integer from 1 through 6. These are equally likely for red. These are equally likely for green. So each of these individual cells will be equally likely. Each individual cell is equally likely. In a way, each individual cell here in the body corresponds to an ordered pair. So for example, red 1, green 1, that gives a sum of 2. Red 1, green 2, that gives a sum of 3. Red 2, green 1 also gives a sum of 3, but it's a different ordered pair for red and green. Still, we get the same sum. Now notice that if you look for common sums, they lie on these skew diagonals here. There's only one way to get a sum of 2. That's snake eyes, 1 and 1. There are 2 ways to get a 3. Red 2, green 1, and red 1, green 2. I'll do some marking. There are 3 ways to get a 4. 3 and 1, and then 2 and 2, doubles, and then 1 and 3. 4 ways to get a 5. 5 ways to get a 6. 6 ways to get a 7. That's the most likely value. There are 6 ways to get a 7. And so the probability of getting a 7 on a random roll of 2 dice would be 6 out of 36, or 1/6. Remember, there are 36 ordered pairs in here, and there are 36 cells in here. 36 equally likely outcomes corresponding to these ordered pairs. But then after the 7, then the sums become less likely. There are 5 8s, just as there were 5 6s. There are 4 9s, just as there were 4 5s. We have symmetry here. We have 3 10s, just as there were 3 4s. We have 2 11s, just as there were 2 3s. And we have 1 12, just as there was 1 2. So there's symmetry about this skew diagonal here along the 7s. Okay, so here's our table of sample sums. Next to it, I have the table of sample means or averages. And remember, ultimately, we're going to use the central limit theorem to analyze means. So even though we're used to sums, we're going to focus more on this in terms of the theory. Okay, the sample sums can be integers between 2 and 12. The sample averages can be between 1 and 6. The lowest average you can get is 1. That's if you get snake eyes. 1 on red, 1 on green, your average would be 1. The highest average you can get is 6. That's if you get boxcars. The third student got that. Getting a red on 6 and a red on green, that's what this student got. Red on 6, red 6, green 6, sum of 12. Okay, that's an average of 6. Now, if you get a sum of 7, and a lot of students got 7s, right? Lots of students got 7s for sums. It's the most likely sum. Then your average is, well, the sum is 7. You've rolled 2 dice. 7 divided by 2 is 3.5. That's the most common average. It turns out to be the mean of means. It's the expected value of x bar, the sample mean. It's the most likely mean, 3.5. Okay, and the averages can go from 1 through 6, but they can also be these decimals. For example, let's say that you get a 2 and a 1. Let's do this in red. Let's say that you get a 2 on red and a 1 on green. A 2 on red and a 1 on green. That means that your sum, or total, your value for summation x, is going to be 3. You roll a 2 and a 1, Vegas says you rolled a 3 as your sum or total. But your average, or sample mean, will be 1.5. Your sum, 2 plus 1 is 3, but then we divide by 2, right? 2 plus 1 is 3, but you divide by 2, and you get 1.5, which makes sense. If you roll a 2 on the red die and a 1 on the green die, then your average is 1.5. That's your sample mean. All right. Now, what happens if we try to do a histogram or this is called a spike plot, remember. This is called a spike plot which can be more precise and deals with more possible values here. What if we do spike plots for the possible sums and the possible means? Basically, what are their probability distributions? We also call them sampling distributions because if we have like 1 million students rolling dice, then we're going to see something very similar to the theoretical distributions. Okay, so let's talk about these spike plots. The spike plot below describes two sampling distributions at the same time. The distribution of sums, so that's denoted here by summation x. Remember, the sums go from 2 through 12. The possible sums on 2 dice can be any integer from 2 up through 12. 7 is most likely. You see, the highest spike is there. But also, in this big picture, we have a spike plot for the distribution of means, x bar. That's going to be this row over here, where the sample averages, or just the straight up averages, can be between 1 and 6. In fact, the most likely average, the mean of the means, and it's the most likely average, is 3.5. Because if you roll a sum of 7, your sample mean, your average, is 3.5. So notice here that the shape of the distribution for summation x and for x bar, for the sum and for the average on the 2 dice, the shape is the same, but we require different scales. The scale for the sum goes from 2 to 12. The scale for the averages goes from 1 to 6. And notice that the boundary values, 1 and 6, they're the same as for 1 die, right? If you roll 1 die, you can get something between 1 and 6. If you roll 2 dice, or even 2 million dice, the average on 2 dice or 2 million dice will be somewhere between 1 and 6. We're going to talk more about these distributions in the next lesson.
Okay, first of all, are there any questions? I tried to set this up very carefully. I thought dice would be a good example. We've seen these before. Any questions? Any questions? Because it gets deep. All right.
Hi, everyone. We're continuing with our discussion of the central limit theorem, the CLT, for sums and, more importantly, for averages or means. We left off last time with talking about this relative frequency histogram, or spike plot in this case, for the values of x bar, a sample mean. In the case where x bar is the average of a pair of dice when a student rolls a pair of dice. Remember, back here, tables of sums versus means. What was the probability of getting various sums on a pair of dice? The probability of getting a 2 was 1 out of 36. There were 36 cells in here. The probability of getting a sum of 2 on this pair of dice was 1 over 36. The probability of getting a 3 was 2 over 36. Don't worry about simplifying. The probability of 4 was 3 over 36. The probability of 5 was 4 over 36. P of 6 was 5 over 36. P of 7 was 6 over 36, or 1/6. This is the most likely probability. 7 is most likely as a sum. But then the probabilities go down symmetrically. P of 8, we're back to 5 over 36. P of 9 was 4 over 36. P of 10 was 3 over 36. P of 11 was 2 over 36. P of 12 was 1 over 36. So if you do a probability histogram, or in this case a spike plot, you would get this spike plot here, this triangular spike plot, going from 2 through 12, using this summation x as your axis. The sum or total of the 2 dice can be somewhere between 2 and 12, and 7 was most likely. For a triangular distribution like this, the central value is the most likely value. Now, let's say that instead of the sum, we consider the average on the 2 dice. The average can be between 1 and 6. Again, we could roll 2 million dice, and we know the average will be between 1 and 6. Well, we looked at this table of averages. And basically, we get the same kind of distribution as before, except that the distribution is going from 1 to 6, not 2 to 12. But it's the same shape distribution. The probabilities go up steadily, then down symmetrically. So this spike plot as a shape applies also to the X-bar distribution, but the scale is going not from 2 to 12, but from 1 to 6. The most likely average is 3.5. Again, for a triangular distribution, that central value, the mean of this X-bar distribution, 3.5, is also the most likely value for the mean. That's not always the case, but for a triangular distribution like this, the 3.5 here, the mean of the means, the expected value of the sample mean distribution will in fact be the central value and the most likely value. Again, why is it triangular? The probability here for the sum or this average, it's 1 over 36, then 2 over 36, 3 over 36, 4 over 36, 5 over 36, 6 over 36, or 1/6, the most likely, sum 7, or average 3.5, then down 5 over 36, 4 over 36, 3 over 36, 2 over 36, 1 over 36. Again, looking at the 3.5, we can say that the mean of the means, denoted by mu sub x bar, that's the mean of the x bar distribution, the distribution of sample means. I'll explain this more later on. The mean of means is 3.5. It's the same as the Big Daddy mean for the original Big Daddy flat distribution. Mu is also 3.5 over here. And that's no coincidence. Okay, so let's talk more about this idea of sampling, because we can refer to this as both a probability distribution for x bar and also a sampling distribution for x bar. It's the same thing. The idea is if you take many samples, like if you have 1 million students or 1 billion students, then the sampling distribution will very closely resemble this actual theoretical probability distribution. What's the idea there? Okay. Once again, here's our Big Daddy distribution for one die. X is the result when you roll one die. I don't care what color it is. X is the result when you roll one die. We don't know it yet, but we do know its probability distribution. We don't know its value yet, whether it's 1, 2, 3, 4, 5, or 6, but we do know from the outset the probability distribution. We assume it's a discrete uniform distribution on the integers from 1 through 6. Let's call this Big Daddy distribution D. Later on, D might represent some other distribution, but for right now, this is our Big Daddy distribution D, this discrete uniform distribution, the result on rolling one die. Now let's say a student takes a red die and a green die, 2 dice, and rolls them. X sub 1 will be the result on the red die. X sub 2 will be the result on the green die. Right now, I don't know them yet. They're random variables, but they each have this distribution. X bar, the sample mean, is also a random variable. I won't know the value of this yet until I get values for x1 and x2. But I do know that whatever happens, to get the value for x bar, I'm going to add these two values up and divide by 2. Now, even though x has D, this flat distribution, as its Big Daddy distribution, the distribution for x bar is not flat. It's triangular. Go up. It's triangular. It was this over here. Using this blue scale as the scale for x bar, the sample means. Again, x bar has a triangular distribution up here, this guy here, using the bottom scale, the blue scale. All right, so let's talk about some samples. Let's say that we have a big lecture hall of 1,000 students. Don't laugh. Very often in big colleges, you'll have a lecture hall of 1,000 students. That'll be in the hopefully near future when we get back on campus. Imagine 1,000 students, each rolling a pair of dice, maybe a red die and a green die. Basically, each student is taking a sample of size 2 from this Big Daddy distribution over here. Each person takes a sample of size little n equals 2 from D, the original uniform distribution. And then each person finds the sample mean of the 2 dice that person rolls. And then these values here will be the values for X bar, the sample means. So for example, for student number one rolls a red die and a green die. And let's say that for student one, for sample number one, the result on the red die is 2, the result on the green die is 3. Then the sample mean, the result of the sample mean for student number one is 2.5, the average of 2 and 3. For student number two gives us sample number 2. Let's say a 6 on red and a 2 on green. That means that that student's average was 4.0. And so forth. We go through all the students. It may take some time, or maybe they're all doing it simultaneously and they're entering data on their iPhones. But student number 1000, let's say, gets a 1 on red, a 5 on green. That student's average is 3.0. Okay, and let's say that we take these 1000 sample means and we do a spike plot for them, a relative frequency distribution. I claim that the spike plot for the relative frequency distribution for these sample means will very closely resemble this triangular plot over here. Granted, we may have sampling error. Remember, when we were doing sums of dice in our class, we had what, about 25, 30 students or so. We got a fair bit of sampling error, but it was very roughly triangular, very roughly. All right. But with 1,000 students, it'll look much more closely, precisely triangular. With 1 million students, it looked very close to this triangle over here. This triangular distribution with this scale in blue. Okay, that's why I have this in blue over here. All right, so once again, the relative frequency histogram or spike plot for the values of X bar, the sample mean random variable, which varies from student to student in value, should resemble this triangular distribution. And that's because of the law of large numbers, the LLM. The idea that if you have many, many samples, then when you analyze the results from many, many samples, then you're going to get something very close to this probability distribution. In other words, the sampling distribution will be very close to the probability distribution. The distribution from a whole bunch of samples, like 1 million samples, will be very close to the distribution you get from theoretical probability. All right, now I claim that the sampling or probability distribution for X bar has, as its mean, the notation is mu sub X bar, the mean of the X bar distribution, but it's the same as the Big Daddy mean, mu, which is 3.5. Now remember, all the way back up here, right, we had the result on one die. It had this probability distribution, a discrete uniform. Mu, for this Big Daddy distribution, was 3.5. Okay, right here, 3.5 was the mean of the Big Daddy distribution. And it's also the mean for this over here, right? Here was 3.5 over here for X bar. The most likely average is 3.5 for this triangular distribution. It's at the center. Again, for a triangular distribution, the central value is the most likely one. It's not always the case that the central value is most likely. You could have a messed up distribution like this, for example, but for a triangular distribution, yeah, the most likely guy is in the center, 3.5. So it's not surprising that the mean of the X bar distribution is the same as the original mean. So whether you're rolling 1 die or 2 dice or 2 million dice, then the expected value of the sample mean, that is the value that the sample means will tend to center around. The value that the sample means from the samples will tend to center around will be 3.5. Whether it's 1 die, 2 dice, or 2 million dice, the center will be 3.5. In practice, if you have 1 million samples, it'll be very close to 3.5. Now, all the way for 1 die, I told you that the standard deviation for the flat top distribution for 1 die, sigma was about 1.7. It was about this over here. And this was based on the optional handwritten formulas and calculations from lesson 16. So you didn't have to know how to figure this out. just take this on faith, that sigma was about 1.7 for this original distribution. But that's not the measure of spread for the new X bar distribution. So even though the mean for the X bar distribution is the same as the Big Daddy mean for the original distribution, 3.5 here, it is not true that sigma for the X bar distribution will be the same as sigma before. Now, the standard deviation of the X bar distribution, the distribution of sample means, that's called the standard error. The standard error, or SE. But again, it's the standard deviation of the X bar distribution. These terms are interchangeable if you're referring to the X bar distribution. Now this formula for standard error, the standard dev for the X bar distribution, it's not just sigma, the way that this was just mu. It's not just sigma. It's sigma over the square root of n. So to compute the standard dev for the X bar distribution, the standard error, you take 1.7078 sigma for the Big Daddy distribution for one die, and you divide by the square root of the sample size, which was 2 in this case. Each student is rolling each student is rolling 2 dice. Each student has a sample size of 2. That's different from the number of samples. We're talking about the sample size, the number of dice that's rolled by each student. 1.7078 divided by the square root of 2 is about 1.2076. And this is going to be the standard deviation of the X bar distribution, or the standard error. The standard error. This will always be less than that. It will always be less than the Big Daddy standard deviation. And why is that? Because as you roll more and more dice, as you go from 1 die to 2 dice to 4 dice to 2 million dice, then the distribution of averages will be more tightly clustered around the 3.5. So you're going to get less spread. As n increases, as the sample size, the number of dice increases, 2 dice, 4 dice, 8 dice, 2 million dice, that's going to have a lowering impact on the standard error. And this will become a lower and lower number. It's going to go down. As n approaches infinity, this whole thing approaches 0. We're going to get very tight clustering around the 3.5 as n gets bigger and bigger and bigger. We'll talk about this more in the next lesson.
All right, first off, we have a lot of deep ideas here, right? So we have the mean of means, right? Mu sub x bar, which is mu, and the standard error of the mean. Okay, the standard deviation of the x bar distribution, which is not just sigma, it's sigma over root n. Again, we'll talk more in the next lesson. Any questions for now? Any questions for now? Okay.
Hi, everyone. We're continuing with the central limit theorem, the CLT, for sums, but especially means or averages. In the beginning, we talked about this Big Daddy distribution D, which was the distribution for the result of one die rule. It was a uniform standard die distribution, a discrete uniform distribution. The probability of 1 was 1/6, and in fact, that was a probability for each of these values from 1 through 6. Discrete uniform, 1/6 apiece. The mean of this distribution, mu, was 3.5. From either the zigzag, or because this was discrete uniform, you could just add these up and divide by 6. Also, the standard deviation was about 1.7. That was discussed in optional handwritten notes in lesson 16. For now, take that on faith. Now, when we consider the spike plot for this probability distribution, it's sort of taking the place of a probability histogram. The spike plot has a flat top. We have flat tops here, right? Discrete uniform. Probability of mass 1/6 for the integers from 1 through 6. That's if the sample size is 1. If you have 1 student, that student rolls a die once. Here's the probability distribution. But what if instead of 1 die, the student rolls 2 dice, say a red die and a green die? what's the probability distribution for the average on the two dice, the sample mean of the two dice? The two dice represent a sample. It's a sample of size 2 from this Big Daddy distribution. The probability distribution for X bar, if you have two dice and we're considering their average value, looks triangular, like so. Now, like for this Big Daddy distribution, the mean of the distribution of sample means is at 3.5. Here's 3.5 over here, which is the same as the mean for the Big Daddy distribution, 3.5. But notice that the spread is decreased here. It appears that these average values from 1 through 6, it appears that these average values are more tightly clustered around the 3.5 here in the n equals 2 case than over here in the n equals 1 case. It appears that the standard deviation of the X bar distribution has decreased as we go from n equals 1 to n equals 2. And that does seem to make sense. So the sampling distribution for the X bar distribution, that's where we have n equals 2 dice. The mean for the X bar distribution, mu sub X bar, was Big Daddy mu, 3.5, the same as for one die and its distribution. The standard error, or the standard deviation for the X bar distribution, is given not by sigma, the Big Daddy standard dev, but by sigma over the square root of n. It's the Big Daddy standard deviation from the original one die distribution divided by the square root of n. So the standard error, about 1.2 here, is going to be less than the original standard D for one die, which was about 1.7. As n increases, as the sample size increases, as more dice are rolled, from 1 die to 2 dice to 4 dice to 2 million dice, the standard error, the spread, will decrease, and we're going to see greater clustering around the 3.5. Again, sigma sub X bar is also called the standard error, or SE, of the mean. As the sample size little n increases, the standard error, or the standard dev of the X bar distribution, sigma sub X bar, decreases. Notice that the probability of mass for the triangular distribution is more tightly clustered around X bar equals 3.5, here for n equals 2 than for n equals 1. That's what we saw over here. We had greater clustering around X bar equals 3.5 over here than over here. Here we had greater spread. So in the n equals 2 case, the average of the dice is more likely to be close to 3.5, the mean of the original distribution. There is tighter clustering. Now as n, the number of dice in the sample, increases, what's going to happen to the shape of the sampling distribution, or probability distribution, for X bar? Okay, here's n equals 1 die, here's n equals 2 dice. What happens if we go to 4 dice, 8 dice, and so forth? Well, for one thing, we're going to get less spread. We're going to get greater clustering around the 3.5. But also, look at the way that the shapes are changing. We started with a flat top uniform distribution for n equals 1. For n equals 2 dice, we got this triangular distribution. Take a guess. As we go on to 4, 8, 16, 32 dice, where we really make it official, what shape do you think we're going to approach? The shape of the distribution of sample means, the probability distribution of means. What shape will that approach? It's right here. Normal. We're going to approach a normal. 4 dice. Tighter clustering around 3.5 is looking a lot more bell-shaped. 8 dice. N equals 8. Even greater clustering around X bar equals 3.5, even more bell-shaped. N equals 16. Even tighter clustering about 3.5, less spread. Standard error is decreasing, even more bell-shaped. N equals 32. Very tight clustering around 3.5, very, very bell-shaped. In fact, by the time n gets past 30, like 31, 32, and so forth, it's official. We can call this approximately normal. It turns out that the CLT, the central limit theorem for means or averages, will say this. There is also a CLT for sums, but we're not going to focus on that as much. We're going to focus more on the central limit theorem for means or averages. I'm going to formally introduce this in just a moment. I'm going to tell you the result here first. In the case of n equals 32 dice, what happens if you, or if a machine, let's say, rolls 32 dice with Crayola colors? Then the distribution of sample means will be approximately normal. Hey, this looks pretty bell-shaped. Approximately normal, where the mean is Big Daddy mu, 3.5, the same as for the original distribution over here. It's 3.5. You're centered around 3.5 for all of these cases. The mean is 3.5 for all of these cases. But the standard error, that is the standard dev of the X-bar distribution, it decreases. As n increases, sigma over root n decreases. For n equals 1, it was about 1.7. For n equals 2, it was about 1.2. By the time we get to n equals 32, we're down to about 0.3, a lot lower. But I claim that the CLT for means or averages gives us this result. This distribution you're looking at here, where you're using this X-bar scale, this distribution will be approximately normal. It sure looks bell-shaped, with mean 3.5 and standard deviation or standard error about 0.3. Again, that's the distance between the mean line, I should move this a little bit, between the mean line and either inflection point. It's about 0.3. Seems to make sense. Okay, now going backwards, what is the central limit theorem? What is the statement of the central limit theorem for means or averages? Now, I wouldn't expect anyone to memorize this, but I would expect you to apply this in problems. All right. Again, doing a review of 32 dice, then we'll get to the general statement of the theorem. Actually, we may wait a while, like a few days, until we get to the statement of the theorem. But going back to 32 dice, let's do a recap. The central limit theorem applies when? So I'm kind of introducing bits of the theorem. When does the central limit theorem, the CLT, officially apply? When the sample size, little n, is large enough, and usually the standard is when n, the sample size, is bigger than 30. Now, this is not the result of some formula or algebra. It's just the result of common observation and practice. This is something that pure mathematicians get nervous about, the fact that this does not come from a formula. It comes from observation, from practical observation. In fact, if you look in the case of a die, we get pretty bell-shaped even by 4 or 8, it looks like, even by 16. Certainly by 16, it looks fairly bell-shaped. All right. But n greater than 30 is the standard. So you could have any shape distribution at the beginning. Flat top, it could be really messed up like that. By the time n gets past 30, we can assume a normal approximation will work out. Now, the central limit theorem also applies when the original distribution, Big Daddy D, is approximately normal, regardless of the sample size. Now, over here, since the original distribution was not bell-shaped, we had to wait a while. Maybe not so long, but to make it official, we waited for n to be greater than 30, for the sample size to be greater than 30, before we could officially say that we have about a normal distribution here. Although, yeah, it looked pretty normal even before that, like at 16 even. But if the original distribution is bell-shaped, I'll erase this. What if we have a bell-shaped distribution? Like so. What if we have a bell-shaped distribution? Then the CLT basically kicks in immediately, even at n equals 1. You don't have to rely on a large sample size. If you start with a bell shape, you're dealing with bell shapes all the way, normals. The CLT applies when the original distribution is approximately normal, regardless of sample size. So there are two cases where the CLT applies. Okay, if the sample size is large enough and is greater than 30, regardless of the shape, or regardless of sample size, if you start with something that's roughly normal. So basically, if the sample size is big enough, or you start off normal, then the CLT will apply, and you're dealing with normal distributions with these parameters, mu and sigma over root n as your standard error. According to the CLT for means, if a machine rolls 32 dice, n equals 32, then the sampling distribution for x bar is approximately normal. Okay, this is the same guy I showed you before. Let's describe him. The sampling distribution for x bar has, as its mean, mu sub x bar, is the same as the Big Daddy mean, mu, for the original uniform distribution, 3.5. The mean is 3.5. The mean of the mean distribution is 3.5. The standard error, or the standard dev, of the sample mean distribution is not sigma, but sigma over the square root of n. Big Daddy sigma, for the uniform distribution, it was about 1.7078. I set that up here. But you have to take that 1.7078 and divide it by the square root of 32, which was between 5 and 6. This fraction ends up being a lot less, about 0.3. 0.3 is way less than 1.7. It's about a fifth or a sixth of 1.7. It's way down. So we're getting much tighter clustering of this distribution about the 3.5 here, the mean, as opposed to up here, where it was a lot more spread out. Here's a lot more spread out. Standard dev here was 1.7. Standard dev down here, 0.3. All right, so the CLT for means tells us this result, that the sample mean distribution was approximately normal, with mean mu sub x bar, same as Big Daddy mu, 3.5. Sigma sub x bar is not Big Daddy sigma, it's not 1.7, it's more like 0.3. I like to write out 5 sig figs just to be safe. So basically, we expect the sample mean to be very close to 3.5. If a machine rolls 32 dice, we expect the sample mean to be very close to 3.5. And why is that? Well, think about it. If you have a machine rolling 32 dice, or better yet, imagine a machine rolling 1,000,000 dice, n equals 1,000,000. What do you expect to see? You see 1,000,000 randomly thrown dice on the ground. What do you expect to see? A big mess, right? But what do you expect to see? You expect to see about a sixth ones by the law of large numbers, about a sixth twos, about a sixth threes, about a sixth fours, about a sixth fives, about a sixth sixes. So it's kind of like uniform. So you kind of expect, kind of a uniform distribution between ones through sixes, right? But what about the average? What's that going to tell us about the average? Well, we have about a sixth ones, about a sixth sixes. The number of ones and the number of sixes should closely balance each other out for 1,000,000 dice. So don't you think the ones and the sixes will basically balance each other out? And what do they balance out to? What do they average out to? 3.5. What about the twos and the fives? You should have about equal numbers of those. Again, they'll tend to balance out towards 3.5, strongly so. What about the threes and the fours? Well, they'll average out to 3.5. But that's why we expect the sample mean to be very close to 3.5 if we have many dice, because we expect high and low numbers to have a strong tendency to balance each other out. So for example, the ones and the sixes will balance each other out, the twos and the fives, and the threes and the fours. So we have a strong tendency for the average overall to balance out to 3.5. We have strong balancing effects. The standard error is about 0.3, which is way less than the 1.7 that we started out with for Big Daddy sigma. The standard dev for the original uniform distribution, n equals 1 die. So that was an application of the CLT to the case of 32 dice. As I promised, next time, it could be a few days from now, next time, we're going to see the statement of the CLT and see where all this stuff came from. Until then.
Okay, so I want to say the same until next time. That's all. It's 9:34. We're on time. A lot of deep ideas today, but I was trying to build up examples. Any questions? We'll continue on, and you might want to wait on the homework for this stuff until next time. This was 22, right? Right. You can do 21, but 22 we're still working on. All right, so that's all. I will stick around for questions if you have questions so far on the homework, but that's all. I'm still recording. But I'll see you next time. All right. In the meantime, did you have any questions about either today or maybe the homework or the lecturing last time? Okay, so I can go over some questions. All right. All right. So, and let me know if you want me to stop the recording. All right. Lesson 22. What number? Oh, so you want a preview, right? Okay, so this would be like a preview. Oh, well, yeah. Let's see, it's 2. How many do we have here? Well, let's discuss this. Let's discuss this. All right. Okay, a large lecture class takes a test. Oh, okay. Okay, so I'm going to lecture on this on Wednesday. So let's make a deal. Why don't we hold off until the lecture on Wednesday, because I need to introduce this to the class on Wednesday. And if you have a question about this, can we address this on Wednesday after class? Okay. Oh yes, because I feel uncomfortable doing a question before we even cover the lesson. I'd like to give students a chance. Let's give students a chance. But I appreciate that you're caught up. All right. Of course, if you have questions about the wording or about the concept, right? Okay, but let's take some time. I'll do some more examples on Wednesday. Any questions? Any questions? I would tend to focus on 19, 20, and 21 for tonight. So, okay, 21C, all right. Okay, so I guess this one, right? Yeah, okay, so 21, 1C. Right. So find the probability that X is between 60 inches and 72 inches, I believe for American men, right? Because we did American women in the lecture. All right. So what's the probability that a random American man is between 60 inches or 5 feet tall and 72 inches or 6 feet tall? All right. First, let's write down the corresponding probability expression for Z. Okay. So you need to find the Z scores for this and for this. All right. So for 60 inches, okay, the corresponding Z score is given by, the formula is X minus mu all over sigma. X is the number of interest, the 60 inches here, minus, okay, mu, the mean for men now is 70 inches, divided by the standard deviation up here was 4 inches. Negative 10/4, I think that's negative 2.50. That's exact. I think it's negative 2.50. 60 inches is below the mean, so it better be negative. I think it's negative 2.50. And the hint suggests that, yeah. That's consistent with my hint over here. Okay, my hints will not be misleading. my hints will be useful up here. All right. And then you do a similar calculation for 72. Show me the work, and you should get 0.50. So show me the work for that. Right. And do I have you draw the pictures? Well, the picture helps, picture helps. So here's negative 2.5 as a Z-score. Negative 2.50. The Z-score for 72 inches, I guess, is positive 0.50, but show the work for that. That'll be like here. Again, even though I don't say so, I think I would encourage people to draw a picture. You don't have to be, Monet or anything, but I think this helps. Now we want an in-between probability. So we want this shaded region in here, this piano-looking thing, okay, between these two values. Okay, so we need to take this probability or area and subtract off this probability or area, and they're given up here. 0.6915 for the bigger area over here, and 0.0062 for the smaller area over here. Okay, and then you would subtract to give the result. Okay, so subtract in order. All right, and see if it makes sense. Okay. Oh, write the corresponding probability expression for Z. Okay, so that's part of the work. I'll put that in red. So it would be the probability that Z is between, okay, instead of 60 inches, instead of x equals 60 inches, we want Z equals negative 2.50. Okay, instead of 72 inches, I guess we get positive 0.50 as the corresponding Z score for that. So here's the corresponding probability expression for Z. And the answer for this will be the same as the answer for that. The idea is that we're simplifying. When you go from here to here, kind of simplifying the problem, and you can use these hints that you can get from tables, for example. Okay, so I hope I give you a roadmap. Okay, that's most of the solution. Okay, but that is the roadmap. Okay, any follow-ups on this? Any questions? Oh, 20C. Okay, so that, anyway, that's 21C. That's the roadmap for 21C. 20C. 20C. You mean 1C? 1C? 21C. Number, lesson 20, question 1, part C. Sounds like Battleship. All right.
Yeah, sorry.
Right, okay. Explain why. Oh, yeah. This is a tricky one. All right. So in part A, you should have shown this. So in part A, oops. You should have drawn a picture like this. Again, you don't have to be Monet or anything, but negative 0.48. I know this is part A, but negative 0.48 is over here. And part A is referring to a left tail probability. And this left tail probability is going to be the 0.3156, which makes sense. This looks like about a third of the total area under the curve. Now over here, going straight to C, maybe we'll put this in red just to avoid confusion. Put this in red. All right. Find the probability that Z is, oh, I should put the Z here. Find the probability that Z is greater than 0.48. Okay, I'll draw this here. So positive 0.48 is going to be over here to the right of the 0. A picture should show that. You're to the right of that hilltop. This time we want a right tail probability. We want the probability associated with Z scores greater than 0.48. We want this piece over here. Oh, okay.
Sorry, I got confused with the pages.
But you know what? My explanation for 1C, that's the logic behind 2C as well. So basically, why are these equal? These are going to be equal, by the way. They're going to be equal by the S word, which is symmetry.
So yeah, symmetry. I just wanted to make sure that like how I have it written out was correct. Like I got the graph and everything and I understood that, but I just wanted to make sure that my P of Z, all of that lines up correct.
Yeah, well, the idea is the same, but the pictures look different. So on number 2, I'll shift to purple here. Okay, so number 2, you're given this big slab, right? So the probability of Z is less than 2. That's this big slab over here, about 98% of the area under the curve. And then for here, okay, so how's the picture look? Z is greater than negative 2. But again, it's by symmetry. So it's just that here's a big number. Here, it's about 0.98 over here. Here, the 0.98 is to the right. But the idea behind a 2C is the same as the idea behind 1C. It's just that here we're dealing with small areas. Here we're dealing with big areas. But the fundamental ideas are the same. And for the explaining why, one word, symmetry. I'll take that one word, symmetry, for the explanation.
Oh, okay. I just wanted to make sure that that's all you needed because I was trying to write out like the equation, I guess.
Oh,
I
no,
don't know what you
no.
call it, but I was like, I don't know how to do that.
Yeah, the explanation, I'll take one word, symmetry. Although it's true that,
Beautiful.
For many problems, like for interpretation problems, I would prefer complete proper English sentences. But for here, I'll take the word symmetry for the explanation.
Okay, perfect. Yeah, I was trying to write the P parentheses Z is greater than -2, and I was like, I don't know if I wrote it correctly. So symmetry works. I've got it.
Oh, right. No, there's no deep connection here or anything. Um, in fact, really the only formula thing you can say is, well, this is going to be the same as that. It's an equal sign. This guy will be equal to this guy. Okay, but that's about as deep as the formulas go.
Perfect. Thank you.
You're welcome. Yes. Okay. Any other questions? All right. Okay. Take care. Any questions? Any questions? Okay, so let's do this. Take care, everyone. So let's do this. I'm going to pause the recording. I'll come back and I'll come back in 9:50. So at 9:50, if something comes to your mind, then come back and talk to me or chat at me. But let's return at 9:50. Okay. So I'll be back at 9:50. Otherwise, thank you for your perseverance. It's been a long night, but all right. I'll pause recording. Okay. So see you maybe at 9:50 or on Wednesday.